Okay, this is IGCSE Physics 062542, February, March 2017. That's 7 years ago, almost, that's not 7.5 years ago from today. Um, so the people who did this paper were probably working their jobs today. It's crazy, man. Okay, anyway, state two ways in which evaporation is different from boiling. Okay, this is easy. You guys know evaporation takes place, or you have to say evaporation. Evaporation takes place at any temp, right? And then we know that evaporation causes cooling. You guys know when you sweat and the sweat evaporates, your body cools down. So evaporation takes place at any temperature. It takes place at the surface, takes thermal energy, lowers temperature. Okay, whatever. No bubbles, lowers temperature. Okay, guys, any of these, I took this one and this one. It's fine. Give one example of a change of state which does not involve boiling or evaporation. I just melting. Oh, they said example. Ah, they didn't say what's the name of the process. Ah, okay, okay. Yeah, yeah, okay. Yeah, I guess they want like what is it? Okay, yeah. I think they just mean like an example, as in like, oh, from solid to liquid. Wow. And you could put like melting. Honestly, if you get this wrong, I don't know what to tell you, wallah. Um, melting. Oh, melting is correct. Oh, okay. Okay. Yeah, if you get this wrong, wallah, honestly, I think it's over, wallah. You should drop out. The graph in figure 5.1 shows the variation of temperature with time for a substance that is initially liquid. Okay, state was taking place at points A, B, and C, and you should say what changes of state, if any, are taking place. You guys should always know at the plateaus, at the straight part, you have two states. Okay, and the change of state always occurs at the plateau, at the we call it plateaus. Plateau is when you have a straight line. Okay, that's not straight, but you get me. So at point A, we're just it's losing kinetic energy, I guess. And then at point B, what's happening? If it was liquid, so of course it's decreasing temperature, it's going to solid. So what's happening? Freezing. And what is taking place? Freezing and gaining potential energy, I guess. And then point C, what's happening? It's losing more kinetic energy. Or molecules are getting closer. I want to see what the marking scheme says. So liquid cooling. Ah, free. Okay. So you don't care about. Okay, what I said is basically the same thing, but okay, we can say it. Point A, the liquid is just cooling. It's decreasing its temperature until it reaches what the freezing point where it starts to freeze. Yeah. And then at point C, the solid cools. Why the first word matters is because here it's a liquid, here it's a solid. So if you just say cooling, need to be more specific. So you can say liquid cooling, then there it's solid cooling, and then freezing. You don't have to say liquid freezing because a solid doesn't freeze, guys. Okay, so you can just say freezing. It's just why the graph is steeper at point C than at point A. That means point C here is cooling easier. What does it mean when something is cooling easier? That means it has a lower C. What's our C? Heat capacity. Remember, heat capacity is how much energy you need to raise to raise or decrease the temperature by 1 degree Celsius. If you have a high C, that means you need more energy. Okay, and since here it's cooling faster, that means it has a lower C, and here it has a higher C because it's taking longer. So it needs more energy. Okay, so the solid, we could say the solid. You don't say has a lower C, no, has a lower heat capacity than the liquid. Tra- here's one portion. Yeah, so here the specific heat capacity of the liquid is greater than the solid, or you can just say the other way around. It's the solids one is lower than the liquid. Okay, we also have question 9. Okay, figure 9.1. Let me go down to the mark scheme. Oh yeah, let's see. So figure 9.1 shows a graph of current against potential difference. So the IV graph of a filament lamp. State what happens to the resistance as the potential difference changes from 0 to 1. So over here, from 1 to 8. Yeah. One thing, without even looking at the graph, you should know that the filament lamp has this graph. It obeys Ohm's law, so it has a constant resistance until when current increases too much, the resistance is going to begin increasing. Why is it constant resistance? Because the slope, this is a straight line segment. This segment is straight up until 1, right? So the slope is constant, so the resistance is constant. So from 0 to 1, the resistance is constant. How about after 1? What happens to the filament lamp? Look, it starts to curve. So that means the resistance increases. Okay. At normal brightness, the potential difference across the lamp is 8 volts. Calculate for normal brightness the resistance of the lamp. We're saying normal brightness. So not when you start increasing the current. No, no, no. Okay, so basically, to find the resistance, we have to do R is equal to V over I. They give us the voltage is 8. How much is the current at? They're saying the normal brightness is at 8 volts. So for normal brightness, how much is the resistance? So you go to 8 volts. To find the resistance, we need V over I. So we go to 8 over here, which is going to be 0.72, because you have 0.2 and 10 blanks in between them. So 0.2 over 10 is 0.02. So it goes up to 0.62, 0.64, 0.66, 0.68, 0.70, 0.72. Okay, so you're going to do 8 over 0.72. It's going to be equal to, let's see, 8 divided by 0.72. Uh, L, 11. Okay, I guess we want two significant figures. 11.1. So it's just going to be 11 ohm. Let's see how much. I is equal to V. Okay, formula, a number, 11 ohm. Yes. Okay. Calculate the power of the lamp. P is equal to IV. And remember, here we're saying for normal brightness. So what's the current? We said 0.72 times the voltage, which is 8. So let's see, 0.72 times 8, 5.76. I guess, since this one's 2SF, I guess this one should also be 2SF, 5.8 watts. Let's see, 5.8 watts. Okay, P equals IV, 5.8. Okay, yeah. Or you could use RI squared, which is completely correct, guys. Uh, this is completely fine. Okay. 5 of these lamps operating at normal brightness are connected in parallel to a power supply. Determine the EMF of this power supply. Remember that we're talking about normal brightness. So over here, we're saying 8 volts, right? So this one's 8 volts, this one's 8 volts, this one's 8 volts, this one's 8 volts, this one's 8 volts. So how much is going to be in the power supply? Is it going to be 40? If you said 40, then it's wrong. Okay, it's wrong. Remember, it's in parallel. Okay? In parallel, voltages are the same. So if this is 8, 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 this is 8. So how much is this? It's also 8 volts, okay? To 2SF, 8.0 volts, okay? 8.0. The current from the power supply. The current, however, if they're in parallel, they add up. We know that at 8 volts, the current is 0.72, right? So if this is 0.72, this is 0.72, this is 0.72, this is 0.72, this is also 0.72. So how much is going to be the power supply? If you said 0.72, then it's wrong. In parallel, you add up currents. They're not the same. So 0.72 times 5, or just 0.72 plus 0.72 plus 0.72 plus 0.72 plus 0.72 also works. So you can just say 5 times 0.72 is equal to, let's see, 3.6. So the current is 3.6 ampere. There you go. That's it for question 5 and 9. Thank you so much for watching, and good luck.